Are you still awake? Good. So we are moving on to a new session. I was very surprised. I want to thank the MSA for accepting this session. This is a session mainly related to how minerals together form rocks, for how we interrogate rocks, to understand the architecture and the dynamics of the Earth's crust, especially the continental crust, which is the realm that we live on as terrestrial animals, because we did not colonize the oceans yet. We are polluting them very well, on the contrary. But knowing the Earth's crust, continental crust, is fundamentally strategic for mankind. And many other sessions before, the speakers before already reminded the importance to understand this realm. And now we have two exceptional speakers. I'm going to introduce them, both of them now, because both talks somehow belong to the same story. Othmar will be the first, speaking about mainly the lower crust, and then Roberta is going to bring us closer to the surface. So therefore, the two speakers are Othmar Muntener, who is a professor of petrology at the University of Lausanne, Switzerland, who is going to guide us in the lower crust formation and differentiation constrained by field studies and experimental petrology. And then we'll be guided by Roberta Radnick, who is professor also of petrology at the University of California, Santa Barbara, and also she has been working a lot for a long time at the University of Maryland, so therefore welcome back home. And she is going to guide us in the Earth's continents through time. So I leave the stage to the first speaker, followed by Roberta, and then we have the question.
It's a great pleasure to be here, and I want to thank the organizers to invite me to this symposium. And I hope to give you a flavor first, why I think we're still going out to the field and look at rocks. To give you a picture of the Torres del Paine National Park, and many of us, they just want to know how these granites form and how big the volume is, okay? And it's my conviction that we need to understand the processes at depth to understand these things that we like so much. And so this contribution is largely a collaborative project for many, many years with Peter Ulmer, and since a couple of years with Mattia Pistone, because we had the crazy idea to go to one of the most famous lower crustal section and to propose a drilling project there. And a lot of PhD students, postdocs now, professors, and I will come back to them in a few minutes. And so the lower crust formation, it's very simple. You know, you take a couple of papers and you see boxes, how the crust is composed, okay? As you see, you need a few constraints to satisfy. For example, the heat flow from the mantle and the heat flow that we measure at the surface. We should satisfy seismic velocity constraints, but you see there is quite some differences first in the thickness of the continental crust, and then also the kind of reservoirs that we could find. We could either say upper crust and lower crust, as Brad Hacker proposed, or we take the original proposals by Radnick and co-workers, which came up with lower, middle, and upper crust. But all of these box models, they don't show temporal evolution. How do we get there, okay? And is there inside a box, what is the vertical variability? And so I found it intriguing to dig a little bit in what people think of magmatic systems. And it's equally simple and controversial at the same time. Okay? Here you see snapshots through time-integrated transcrustal magmatic systems. And some of them, they look like silly and dikey. Some of them look like silly and mushy, okay, mush systems, or some others, they look like blobby and dikey, but still, do they catch the same bulk crust composition? While a volcano, maybe on a geological timescale, we could argue that this is a pretty nice integrated picture from low silica areas to high silica areas. We are much more in the darkness when we look at these sections or even these sections where old material pops out of the diagrams. So if we go now to these famous chemical diagrams, I show you two of them, silica against magnesium number to the left from the Ivrea zone, and to the right from compiled data from amphibolite and granulite facies. And usually, before you draw such diagrams, you make your statistics right. You should analyze more than 1,000 bulk rocks to see a tendency from more primitive compositions to more evolved compositions. But in general, such diagrams, they look quite similar, and it's very difficult to extract the processes. Even if we put on estimates for the bulk crust, here a compilation from Brad Hacker, or basalts from the Cascades, and this is the Ivrea bulks, there is still quite a big variability on these type of diagrams. So, yes, the Earth's crust is unique, as Mattia said, but there is a lot of open questions, okay? And so, is this distinction in middle and lower crust useful? Is it necessary? Are there signatures in the bulk rock dataset that constrain or reveal formation processes? How does it change with time? Okay. And does the distribution of heat-producing elements vary with time? And in the end, can experimental data constrain lower crustal processes? How can we read the data sets if we go back to the Archean, where we probably see much less, it looks more homogenized, and is it representing mixing, relamination, or magmatic additions? Okay. So there's a lot of questions, and a few of them I try to address in this presentation by first going to the famous Ivrea zone at the border between Switzerland and Italy, one of the best studied lower crustal sections worldwide, I guess. And what we did is we compiled the bulk rock data that are existing and used digitized maps and see what is the proportions of rocks that are exposed in this area. So this would be the lower crust, about 10 kilobars, and here we see sediments. You basically get an entire section. And for the Ivrea bulk crust, we ignored the sediments on top. Why the Ivrea? When we look at pressure temperature estimates for the Ivrea along 3 sections from the northeast to the southwest, 2 of them, they are quite nicely fitting sort of a normal geobaric gradient. Here we would be 10 kilo, that's a 10 kilometers distance, and we would get gradients, pressure gradients, about 0.36 kilobar per kilometer. Here we get 0.42, and except this section here in the northeast, which is clearly thinned out during a later stage, but it's a reasonable assumption that most of it from the Permian is still preserved. The nice thing about this section is that we get magmatic systems from the base of the crust to the upper crust and even to the volcanics. So we can distinguish old crust in here, pre-Permian, compared to what was added in the Permian and ask ourselves, is there a difference? Does it look similar? Is it necessary to distinguish the different reservoirs? We did this mass balance, and we came up with a Ivrea bulk composition for the upper crust, which is quite nicely fitting what, for example, Brad Hacker has compiled in terms of silica content, and a mid to lower crust, which is also not too far away from what Brad Hacker made in his re-estimation of the 2011 paper. When we split the composition in pre-Permian and Permian magmatism, you see big differences. You see only 48% silica, for example, while the bulk crust has 54, and the pre-Permian was on 57. The upper crust is more silicic, so clearly the magmatic addition adds chemistry which is different from what was pre-existing. For the Ivrea case, we could argue maybe with the 2 reservoir model that would satisfy ourselves. And if we get that contrasting difference in terms of silica content and magnesium number, maybe the Permian magmatic addition develops a geophysically reflective crust, which we didn't have before out of a metasedimentary crust. So how can we disentangle the geochemistry? Okay. Now I split the data that you saw before, silica against magnesium. This is the Permian magmatism, all the added stuff, and this is the old crust. Okay. There is a slight difference that you can see, mainly that some compositions from the magmatic part is not reflected, but in the old crust you get a lot more scatter since they are sediments. So we again add compiled data set, okay, granulite and amphibolite facies, and this looks sort of very similar as we found for the Ivrea zone. We could add cascade volcanics, okay, which also cover most of the range that we see here. And still, in this data set, without knowing what is magmatic, what is pre-existing, it's very hard to figure out, to separate igneous processes versus metasedimentary processes. To calculate the average, this is always easy, okay? You will find yourself somewhere in the middle, because all these compartments will help to find a bulk composition in the center. So mixing of and igneous differentiation in big data sets is very difficult to distinguish. So when we now put on, I go back, so another chemical diagram, silica against the alumina saturation index to see if we get paraluminous compositions. This is the magmatic data from the Permian, from the Ivrea zone, and this is the old crust, typically quite scattery because of a lot of sediments. So we see clearly a temporal evolution. We go from this stage, basically, to something where this one has been added. When we now plot on top here experimental data from fractional and equilibrium crystallization experiments and also calculate silica against the alumina saturation index, you see trends that are strikingly similar to what we see for the Ivrea magmatic part. So the black dots, these are experimental cumulates. The blue ones, they are liquids from hydrous experiments, and everything which is red is fractional crystallization of dry magmas. So you might wonder, how can we do this simulation of an entire magmatic system from gabbros to granites? So first of all, what you need is a couple of PhD students who like failures. The second thing is what you need is you should not hope that you can get out of every PhD 3 papers because there are too many failures. And in the end, start thinking how can we get fractionated experiments compared to equilibrium ones. And this is shown here. Here. So this is sort of the classical approach, the speedy approach, to say, you take one composition, you vary P and T, you get a grid, and you get a first answer. But if you want to see how magmas evolve, maybe fractionation is important. So you have one starting material, you get one experiment with crystals and melt, then you have to remix the starting composition, do the same thing over and over and over again, and after 4 years, when you have one series, the PhD is finished, and you still don't know how you can interpret all this data, so you need more students. The experimental products, they are very nice, okay? So here we can still believe that equilibrium thermodynamics works somehow, because we use textures and homogeneous compositions, but those of you who have sharp eyes, they can clearly see some minerals are zoned. Okay, so we do a simplification, but the nice thing is, since this is phase equilibria controlled, usually the liquid will evolve in each step when we remix the starting compositions. And you get nice increase in water while you crystallize anhydrous phases. So basically, you see an enrichment in water if you do enough experiments. So if we look at the results compared to nature, classical geochemical diagrams, the TAS or silica against potassium, we cover with these experiments basically most of the magmas that would occur. And you can also fit them, for example, cascades and lamello in gray here. The experiments sort of nicely reproduce in major elements what can be done, or what has been done in nature. And we call this, we could simulate the liquid line of descent with these fractionated experiments. And they sometimes create a lot of troubles. And this is a figure that Tom Sisson gave to me because I had discussions with years with him. Because when we did these experiments, silica against the alumina saturation index, and we finished in paraluminous compositions here, he thought our experiments are wrong. And they reproduced it, and they found the same thing. So this is what Ross said before. It's nice. Another group has done the same thing. Either we did the same mistakes together, or the results are somehow credible. So that fractional crystallization would produce and give you paraluminous compositions if you do it at high pressure. So one way out, most of the granites there in the middle here, is that we would do mixing all the time with granites and primitive mafic magmas on a data set that is contoured for about 6,000 continental margin analyses. Okay? So these mixing chords here would bring us to the average composition, for example, of the Cascades or of the Sierra Nevadas. If we go back to the experiments, what do we see in each experiment? Does this mean 5 minutes? No. Thanks. Okay. So, here is temperature, and this is the proportion of phases that crystallize in every single experiment for magnesium basalt. And what you see is the instantaneous solid composition in every experiment. What is nice for the mafics, you get a series between 1200 and 1050, where you get in each experiment quite a bit of phases that crystallize. Then you get a boring middle with not much crystallization. And again, in lower temperatures, 750 to 900, you get more crystallization with more crustal minerals, amphibole, plagioclase, while here you are dominated by olivine, pyroxenes, and spinel. If you take a different composition, a basaltic andesite, the result looks a bit different, less crystallization in the beginning because you have less magnesium, but the overall crystallization in the crustal part with plagioclase and amphibole is quite similar than for the other compositions. So somehow fractional crystallization converges you to a common crustal composition. We can also look at the accumulated solids. So now we just accumulate, and you could see after all this fractionation step down to 750, we crystallized about 80%. And most of it was olivine and clinopyroxene, but then you get amphibole, spinel, and plagioclase. And this is known for a long time, that you get a lot of crystallization of mafic or ultramafic phases, and one might wonder, when we talk about the crust, how much of this crystallized in the topmost mantle, and we simply cannot distinguish it in geophysical data sets. Okay? So about plagioclase crystallize about 50 to 60% of crystallization. The nice thing is, what you also see is the water content, which increases during fractionation up to values of about 10%, which is probably the limit that you can quench in melt inclusions. But it fits sort of the data that is around, that you can get up to 12% in melt inclusions. We can do the same thing. So this was part of a PhD finish in 2000, and Peter Ulmer added a lot of experiments, and it was published in 2018. 18 years to get the results out, not high speed. The dry stuff worked much faster. Okay? So you see 7 kilobar and 10 kilobar, and you get much more plagioclase, as has to be expected. So this is probably relevant, this dry crystallization for mid-ocean ridges or continental tholliites. But still, we get 15% ultramafic rocks, and then we get gabbro and proxenites before you get these gabbronorite, and very little granite can be formed by dry fractionation. So are these experimental studies relevant to nature? So for this, with Oli Aguts, we looked at the Koistan complex. Oli made many nice papers on the Koistan arc, on the dry part, Chilas, the wet part, where we crystallize clinopyroxene and garnet. And the amazing thing is, if you plot the bulk composition of the cumulates in Koistan, you see all the data here. Okay, you get proxenites, gabbronorite, hornblende gabbronorites, and the plutons. You can take talkeetna, and a similar story can be found. And if you look at the cumulates that are formed by experiments, they nicely reproduce what we see in juvenile continental crust. So fractionation in the deep crust and exposed sections of the deep crust that are purely magmatic have a very nice coincidence in terms of the governing processes. So that inspired to compare natural data with experiments even more. What you see here are arc sections from Oli Aguts' paper in 2014. These are hydrous experiments at 1 GPa, and these are dry experiments on 7 kilobar and 10 kilobars, not GPa, and these are wet ones on 7 kilobars. And the proportions that were estimated in nature fit quite nicely to the proportions that can be produced by experimental petrology. So yes, there is some hopes. Now, just one trace element plot. You know, everything is much more complicated if you go to trace elements, but I'm basically interested in major elements. But what you see here is bulk rock composition in dark of the crust and lower crustal composition in this light field here. The estimates for lower crust are much more variable. The colored symbols here is Ivrea, separated the bulk crust in red, in blue one the pre-Permian one, and in green the Permian addition. And on the bulk crust level, you don't see much difference. If you go to the lower crust, you could see the Ivrea lower crust here, compared to the pre-Permian Ivrea lower crust, very similar, but the magmatic addition is quite different and is halfway similar to what is purely magmatic addition determined in the Koistan arc. So from this, we might speculate that continental magmatism has assimilated some of the crust, but the signal can still be found. So the recommendation basically is, if you look at big data sets, there is some hope that we can figure out what is the magmatic addition to a given terrain to understand how the continental crust really formed. This brings me to the conclusions that the Ivrea, we don't need a distinction between middle and lower crust. The Permian magmatic addition enhances the compositional contrast between bulk upper and lower crust, adding a low silica crust and the silica upper crust, and this might forms geophysical detectable signals by transcrustal magmatism. If you go global, the lower crust incompatible elements are probably dominated by volumetrically minor metasedimentary components, and so the igneous crust may be lost in this geochemical noise. Okay, so I encourage you to look in the future to better see the igneous signature in these terrains. The experimental cumulates, they show a striking similarity to lower crust, and fractional crystallization in the deep upper crust and upper mantle produces this, what we call the cumulate line of descent, which is a very nice analog to understand natural systems if the lower crust is nicely preserved. Thank you very much. The motivation comes out of this. Right? You see these nice places on granites in Patagonia. You see these beautiful outcrops in the Ivrea zone. And to linking these two from a magmatic perspective is a lot of fun. And I hope for the next 100 years, despite all the restrictions we have for society, is that the primary motivation to do the basic research and understand the Earth's crust will continue in this way. Thank you very much.